Yo, can you check if it's live? All right, we're gonna get started. How are y'all today? It's a bit dark outside. Good. All right, cool. All right, so today we're gonna be talking about NLP again. Just quick raise of hands. How many of y'all were here last time? All right, so I'll try to make the recap a bit more comprehensive this time then. So today we're gonna be going through more of the modern stuff, like what people use in practice nowadays. That's transformers. Okay, so quick recap. Training a machine learning model. This is basically every time. So for the people who've been here a while, you can zone out, I guess. So to get the overall structure of how machine learning works in a training loop is there's an architecture, which is your neural network or a model, and that takes in an input and produces an output like a function. But it's special in one way, and that is that it has weights or parameters, and those parameters change what outputs comes out of the model or weighted function. And then once you have a prediction, we basically compare it with what we want it to predict, which is called a label over here. And we get a loss. So the difference between what we want to have it be and what we predicted. And we use that loss to update the initial weights. And when we do this a lot of times, it basically gets better on producing stuff that looks like the labels. So that's a very broad overview of machine learning. And hopefully that recaps the people who weren't here before. And to recap the last workshop, what is natural language processing? Maybe one of y'all want to give it a shot. What is natural language processing? Go ahead.
Where you understand, interpret, and generate human language.
You just read it off. Very clever. Okay. Yeah, that's what he said, where you understand, interpret, and generate human language. And by that, we mean the machine understands, generates, and interprets human language. So an example of that would be a machine understanding what words I'm saying right now and being able to respond to it. So that's an example. So I think we covered last time, it's called tokenizing. So this is where we have to structure the input in such a way that the model can actually use the information. Machines, they don't understand what the words mean, so we have to give it to it in a way that we can use it, and that would be converting the words into numbers. So the first thing we have to do is called tokenizing, and that's where we split up words or sentences into smaller, little sub things, so we can encode it into numbers. So here are three main ways of doing that. First way, the easiest way, is just to split it character level. So this is tokenizing, just split up to every little character in there. And another way is another very easy way, but it has its own issues, which is splitting it up into words. Some issues that one can face is if there's a word that hasn't been in the training set, it won't know what it means. So that's an issue that I can face. So something that kind of supports that issue is sub-word level tokenizing, and that's where you divide it up into more common subwords. So it's more likely to not miss big words. Okay. So I don't have that slide here, but what we do after this is we can simply just encode these. So this first letter can just be 0, 1, 2, 3, 4, 5, 6. That's one way of encoding. There are other ways where we can use a neural network to encode it, but we just want it to become a number, so that's the next step. It's called vectorizing. So last time we covered recurrence, and what that basically means is to the left, we basically have a neural network where we have our architecture in the middle, we have our inputs and then our outputs. So here's just simply one pass. And in recurrence, we basically feed in the output and into itself again, and with a different input. I don't think it's really showed in this one. Maybe this one is showed, where we have different inputs and we're just feeding it back into each other. So these are the different variants of using recurrence. These last ones are neural networks. These ones are the recurrence ones. I think. Oh wait, no, whatever. Any questions about this or anything so far? So the main thing that we got here that was different from before was we can produce outputs that vary in size. So that's like the main thing we got there. But there are some limitations to this. And one of them is that, as we can see here, when you keep on passing it down, but you don't like have the inputs going into it, what can happen is when you multiply it a bunch of times, it can kind of forget the earlier information. I don't really have a board, but what basically happens is like when you're updating from the loss, they can't really update the earlier information, so it kind of forgets the earlier information. I know that's pretty broad, but hopefully I can make that more concrete in the next slide. Or like how we can support that problem. So one thing that we do to kind of like assist in producing better results is called attention. And that basically just takes the output from our recurrent neural networks and weights them based on how important they are. So like if I had the words like, how are you? And I was trying to answer that question, we would need to know which words are the most important. And that's what attention does. So maybe in how are you, the most important words can be how and you, and then are. So it's kind of weighting based on how important it is. And then we feed that into like a decode. That's like the idea of attention. Go ahead.
So how does it figure out which words are more important?
That's a great question. So what we do is we basically make this a weighted neural network. So these weights are just weights in the neural network, and we kind of learn it. So what happens here is, as you can see, a special thing about attention is that they are probabilities. They're not just like anything you can weight, like normal neural networks. So what we do is we get these outputs from the neural networks, and then we convert it to probabilities, and then multiply it to the vectors. That sounds pretty abstract when I just say it, but we'll take a look at it. Okay, here's an example of like visualizing it. So like the word the, like the brighter the thing is, the more important it was to the output, which is this side, and this side's the input. So take a look at it. We can see that this word was important to this output sort of thing. This word was kind of important to that one. You can kind of see the relation here. And we're just looking at the weighting for the words and the outputs. Okay. And we're still in recurrent neural networks where we have attention to kind of support that. Later on, I'll show you like a more concrete equation rather than just me saying it out loud. Okay. Any questions so far? I ran through that really quickly, so it's fine if you have questions. All right, quick question for y'all then. What is attention? Just anyone want to go ahead and try to explain it to me? Go ahead.
It's where you put weights on certain words and certain phrases where some words might be more important to the sentence than others.
Yep, that's it. So what he basically said was weighting based on importance to the outputs, kind of. They learned some weighting of it. And the distinction from this to a neural network is that it does it with probabilities rather than just normal numbers. Okay, so the limitation, I kind of mentioned it before, is diminishing influence from like earlier inputs. And the reason why that happens is when we keep on feeding it back into itself, like the hidden unit, the hidden like things that's supposed to contain the older information, it just kind of gets lost as you have many more multiplications, additions. So like they just become less influential. And because of that, when you do your gradient descent to update your weights, it like just doesn't really get the earlier stuff that well. So that problem is basically the forgetting problem where you forget earlier inputs. So that's like a big issue with recurrent neural networks, and that's what we're gonna try to fix with self-attention, which is like the biggest breakthrough in like the last 10 years in machine learning. It looks pretty simple, but what it is, it just like, instead of just attending like for outputs, we attend onto ourselves, like the inputs. So instead of just having one attention weight, we have a matrix of them. So what we'll see here is we'll kind of see like how important are these to itself. So if you take a look, it says hello is important to hello. And love is important to love. But then we can also kind of see what else it kind of is referencing, like it's important to I, like what is it referring to? And then you, also pretty important. So you can kind of get an understanding that it's able to attend to the entire thing rather than just small parts of the input. So that's the main thing here. So before, what we had was only attending to like kind of local things, but now we can attend to everything. So if we continue this on for a long time, it only kind of get local stuff, like smaller area. And the next one, we can get the entirety of it. So that's like the main thing that like, it's the biggest breakthrough in machine learning. And it basically solves the forgetting problem because you don't have anything to forget when you just once you just like do it to yourself, like the whole thing. Any questions about this? Okay. So where this is used, and one of the most like famous machine learning models nowadays, it's called transformers. It's like really complicated. It basically is just the architecture in the earlier training picture I had, the training loop. So here what's happening is we have kind of an amalgamation of a lot of different things. And the main thing here in a transformer is called the multi-head attention. And what that is the self-attention with multiple heads. What that just means is you use different parts of the input and you just combine at the end. So what that allows for is just parallel processing. And that's kind of why it's really important nowadays, because everyone's scaling up everything. And when it's easier and more efficient to use, it's better. So what the transformer solves is two things. One is not forgetting the earlier examples and inputs, or the earlier input. And second is it's more efficient. So to go more in depth into what's happening here, I'll go into the multi-head and I'll give a brief description of everything else. So the feed forward is just a normal neural network that's just multiple layers feeding onto itself. The input embeddings is just like a matrix where there's like encodings. So like it just encodes the input. So it can either be a matrix, like a dictionary, where you get the words and then you encode them, or it can be a neural network where you encode them like that, with numbers already encoded. So that's what the input embeddings is, and the positional encoding. Since some of the positional information can be lost there if you use a neural network, it just is like 1, 2, 3, 4, and you just add it to the sequence. Okay. So to go into the multi-head attention, I'll explain this part. So this is like the whole attention thing. I don't think I really explained softmax, but the general idea of it is it just converts it to a probability. Okay. So the main operation that's happening when you're using attention is the one on the left. And that's where you just have the two matrices multiplying each other, and then you scale it down, and then you do the soft times. So it's kind of shown in this equation on the right. To make it a bit simpler, an example of this could be like, you have the words, how are you? And then you encode it into numbers. And each of these are basically the same thing. Okay. And then we just multiply them together. I'm gonna grab the whiteboard real quick. It'll be easier with this. Sorry.
Those are matrices, right?
Yeah, they are. Sorry about the delay. Okay, sorry about that. Okay, returning to what we were talking about. To make it a bit less dry, I'll just draw out an example. So, an example of this is Q, K, and V are all neural networks. So those are like the outputs are going to be the output of a neural network, and they're all supposed to be the same size and everything. So that's just background information. So let's say we have 3 vectors, 1, 2, 3, 4, and 5, 6. And this can be Q, K, and V. So what's going to happen here is we're going to multiply these two together, and then let's multiply them. So it would be 1 times 3, sure, and 2 times 4, which is 8. In practice, we're going to use matrix multiplication. I'm just using vectors to make it simple. So this would be the first step, matrix multiplication. And then we divide them by what we see over here, which is the square root of the dimension of the key. That sounds pretty crazy to me. When I first read it, what it just means is like how many items are in here, and then we just divide it by the square root of that. So here there's 2 items. So we would multiply it times the square root of 2. I don't remember what that is. The output would be like 3 square root 2, 8 square root 2, 8 square root 2. So why we do, what, go ahead.
Wait, did you say you would divide it by the square root? Would be 3 over the square root of 2?
Oh, yeah. It would be 1 over square root of 2. Thank you for that. So we'll divide it by that. And the reasoning behind why you do that is when you multiply things a lot, they tend to become smaller. And what I mean by that is if you multiply a fraction times a fraction, it becomes a smaller fraction. So what can happen is when you do this a lot, it becomes a 0. And we don't want that. So what we had to do is we have to kind of scale it down a bit, I think. Yeah. We scale it down so it's a bit smaller, because the same thing can happen on the opposite side. If it's too big, it's gonna go on to infinity, because the limit in machines, the representation is kind of limited, and you can only go up to such a big number. So that's why we kind of divide it by this number. So when the matrices are big, it's going to really support that part. Go ahead.
So what was the DK again?
So the DK is a dimension of the key.
Okay.
So
if you had like a 3x4 matrix,
yeah.
what would that be?
If I remember correctly, I think it would just be 4. But you can check the paper for that one. I think it's 4. So you do square root of that. And it's just to scale it down such that it's not too big or it becomes too small. So that would be that part. And then we take softmax, which basically is a exponential weighted average. Sounds complicated. Not weighted average, but it's an exponential thing where it converts into probabilities. I won't go into it because it can look a bit complicated, but just to give a simple example, let's say I have a fraction, 3/4. I want to know how much this fraction is in probabilities, and that would be, that is 3/4. So an example of this can be, like, let's say I have different probabilities for different things. Eraser. It's my hand. So let's say I have a coin toss, and we got heads and tails, right? And we have the numbers 2 and 4, I guess. And that kind of is how many times we had heads, how many times we had tails. So we want to get probability of that. So what we would have to do is we would have to take the 4 and divide it by the sum of these two. So it's pretty self-explanatory. You take 4 divided by 2 plus 4, and then we kind of get how many times we had 4 out of the total. So that's basically what's happening with softmax. But instead of like having 4 just being 4, we take E of it, and it just makes it a bit weighted in a certain direction that weights stuff that have higher values more than stuff that have less values. That's the best way I can explain it without going too much into math. But the idea is you kind of just do this thing where we get the probabilities. And that's how we get our weighting for the attention. I rambled a bit there, but once we take the scale dot product, which is the main thing, we can go back to the transformer. We will add the input and then normalize it. I won't go into normalization. And then we put it into a neural network and then add the previous input. So what this is called, where we're adding it back in, it's called skip connections or a residual connection. And what that does is it has to do with like multiplying things a lot of times over and over. And it just makes it so it doesn't really forget stuff as much. I don't want to go into the math, but it makes the updating process of the training loop a bit easier. And that's kind of the transformer in a sense. So yeah. It was pretty broad overview of the transformer, so don't worry if you don't understand everything. Yeah, you can look at the paper and read it if you had the chance. But the general idea is attention makes it so it can have the whole input as like, it can kind of understand the whole input rather than just small sections of it, and it's quicker. Those are the two main things about transformers. And there's like multiple types of transformers used nowadays. And the reasoning behind that is just because it's really good. And there's 3 main types of transformers. Just normal transformers, where it's just the structure we saw before, just stacked on top of each other a couple of times. Encoder only and decoder only. So to explain what encoder and decoders are, is I kind of showed it last workshop where we had a recurrent neural networks. The first layer acting as an encoder, the second layer acting as a decoder. And why we had that was because the sequences, the output sequences can be variable. So the left side is our decoder, the right side is our encoder. And what happens is we have our input embeddings going to the encoder, and it encodes the information, and then we feed it into our decoder along with the output embeddings. So I'll give a visual understanding of that in the next slide. So we get one output, and then we feed it back into itself, and then we get another one. This is called autoregressive. So this is what all of the transformer models and encoder only and decoder only models do, where it gets an output, feeds it back into itself, and it gets another output and feeds it back into itself. So the special thing about, the main difference between the encoder and decoder is here we have our encoder, which is just one multi-headed attention, and then a neural, like a feed-forward neural network, which is like a normal neural network, and then we get an output. So when you only have the encoder, it only encodes the information, but it does it in a way where it can attend to everything. So if we go back to the attention picture, it will have this whole thing where we have weights for everything. The thing that decoder does is a bit special in that it has to take in the output embeddings. So what it has to do is use a masked multi-headed attention. And what that does is instead of giving all the attention weights, it only gives part of it. So if we go back to the previous slide, what it would do is it would kind of block out this half of the matrix. And the reason for that is it just doesn't know that information. So when you're decoding, you get the output and then you have to feed it back into itself. So when you're training it, you can't have that information there, or you can't assume you have that information. Any questions about that? Anything so far? Cool. All right, so to kind of broadly explain what the three main things about transformers are, is we have a BERT, which is the main transformer, and GPT. GPT is a decoder-only model, where we kind of feed it back into itself every time. And the encoder-only is where we feed it in once, and we just get the encoding of the input. And in decoder, we feed it in input, and then we kind of go back and forth. And the reason for that is the GPT kind of generates new text, and the BERT only encodes it, or the encoder only encodes it. So let's go to this image. So the input to the GPT is the normal sentence, and then a divider, and then the output over and over. So that's kind of a view of how the three main ways that transformers are. And that's just the normal transformer, which is used for like more translation tasks. The encoder only, which is used for more like embedding stuff into semantics, which just means like putting into numbers that means stuff. And a decoder is like more generating output sequences. So it could be like question answering, like GPT does all the time, and like many other tasks. Okay, so now to actually get to like some of the more fun stuff, which is like understanding prompting and like how you train these. So I just took a screenshot of like a data set example. So this would be our system message for our GPT model, and just kind of giving it a role. And this would be the prompt, which is like the input sequence, like what it's asking it to do, generate approximately flat. And this is what it's supposed to produce. So to kind of understand what is going to come from the GPT models, you have to kind of understand how it's trained. So what is the task it's doing? Any question, any answers to that? What is the task it's trying to do? So raise your hand if you think you know what the task the GPT model is trying to do. Great. So to make it a bit more concrete, this section is the input, this section is the label. And every time we feed in an input, it'll generate an output, which is over here. So I put in recite the first law, and then it says a robot may not. So that would be an example of this model architecture producing its prediction. So if we bring it back to the training loop, let's go all the way to the front. We have our inputs to our architecture, we get a prediction, and then we compare it with the label, and then we update the weights. So to bring it back to the data example, this section is our input, this section is our label. So does this help anyone like try to understand like what is the task the GPT model is trying to do? Sorry, what? Yeah, exactly. So specifically, the task that's being trained on is question answering. So we have a question here for a task, I guess, and we get an answer. So what it's going to be learning is to produce these outputs when it has these inputs. So it's just the machine learning task again, but with different labels and different inputs and a different architecture. And the important thing about this architecture is, as I said, it doesn't forget stuff of the earlier inputs, and it's quicker.
You can have multiple inputs, right?
Yeah. So how you can do that is just have dividers between your inputs. So as it's kind of shown here, they utilize a divider for the output. So you can similarly do that with like different symbols. So in that one, we had a system message and then the input. So in OpenAI, they might tell the model to say, you're an assistant model, you must answer in blank ways. And then they'll have the actual person's input attached. So the reason why I was kind of showing you like how it's trained is because it's important to understand what outputs to expect from the model. So when you kind of understand what it was trained on and what task it's doing, it's easier to prompt it to get it to do what you want it to do. So what is prompting? Anyone want to take a guess at what prompting is? Maybe you heard about it on Twitter or something recently. Oh, go ahead, sorry.
Is it like giving like a good input so that will like train the model well?
So you're close. It's not about training, but it's more about using it. Although in training it is called giving it a prompt. As a user of it, you want to prompt it well so you can do well on your task. So it's what he said, where we give it a input such that it produces an output that is kind of similar to what we want it to do. So like if I tell it to do like make code that makes write a paragraph that explains how I can get an A+ in this class, I don't know, something like that. And that would be our input. Like it might just produce some bad output. So the idea of prompting is making your input a bit better and closer to a bit better in the sense of producing better output. So the reason why it's important to understand why the data, how it was trained, is because the output of the model is purely based on what it was trained to do. So if we're asking it to do rocket science, and it was never told anything about rocket science, it won't know anything about it. So it's helpful to understand the limitations of it and also some of the advantages it can have. So also it's important to kind of have a similar structure of how it was trained to do. So if I was trained to I was a cashier, and I was always trained to like click the button whenever I opened the thing, and like only take cash of $1 bills. And if someone just asked me to do like $100 bills, it might be a bit more difficult for me. So you want to kind of do it in a way they were trained to do it. So I'm a cashier, I only take $1 bills for some reason. So just do it the same way to get the most efficient results. So there's a couple of ways to prompt it in a way that will give a better output. And the reason why this is important is because nowadays, a lot of the machine learning tasks have been just boiled down to prompting a GPT model and like getting a nice output. So like, if you heard about companies like, there's some Anthropic, no, companies that use prompting. No. Okay. Anyway, so like the example of this is like there's like tons of new companies that just like their whole business is just prompting GPT. They just prompt it in a way that it can produce good outputs. So like an example of that is the other day, what I did was, which was yesterday actually, for a project I did, I was basically taking in a bunch of trial data from medicine, and I was just asking it, given like patient information, is this a good match for this trial? So like that was the whole thing, but it produced good results, and that's why it's like better than like just like manually doing like logic.
So prompting is basically asking the right question.
Exactly. It's like if you're a manager telling your workers what to do. That's like the best way I think about it. Like if you instruct them in a way they can't understand, they won't give you good outputs. So a couple of the ways that that is really helpful in using like GPT-like models is role playing. And the reason for this is like a lot of the examples are like when they train the model, what they do is they give them a role to play, and that's how they condition the output, meaning that this is going to be something like what the input looks like. So you want to just make it as close to the inputs it was trained on. So an example of this is you're playing the role as a professional writer, write a paragraph that that is blank. So that can be an example of role playing. Just to get a quick hint, how many of y'all use ChatGPT? All right, so y'all probably are familiar with this way of doing things. Like another way of using this is like, you're a 500 IQ person, solve this task for me. And then it actually works, like it produces better results. Another example is called multi-shot prompting. There's always these complicated words to explain these techniques, but what it just means is give examples. Give examples of solving that task. So if you're making a company right now and you're using this sort of technique, like where you're using prompting to like do well on your task, this is probably one of the biggest things you can do to like add value, but something other people can't do. If you can make good examples of an input and an output, you can usually perform a lot better on your task. And an example I showed you is pretty simple. I just ask what is 10 plus 9? I get 19. What is 12 plus 8? I get 20. And then what is 13 plus 6? And this is where the model is supposed to answer. So this is kind of a trivial example, but a more concrete example can be review this resume. And it just has the resume. And then you give an example of you actually reviewing it. And you do that like a couple times. It's going to produce something similar to how you review it. So you effectively automated yourself. And that's just through multi-shot prompting, which is just giving examples. So this is like one of the biggest things about LLMs right now, and that is you can just give nice examples, and it kind of automates the thing.
So you say that if you keep on asking more precise question, the engine improves.
Kind of. So it's like giving more examples of what it's like trying to answer like.
Okay.
Like giving it a similar structure. That's the main thing. So what I would do is like I would have question, like maybe in brackets or something. Like question, and then my question, and then answer. when I provide my example answer, I'll just kind of shorten it. So, and then these will just keep on like a couple of these. And then at the last one, when I'm actually like using the user's question, I'll just plug it in here and then leave this for the model to output. And you can also kind of use this as a way of formatting. So you can use this to like get a nice format. So you give like a couple of examples of like JSON format outputs, and it'll produce a JSON output if it's trained on like that sort of task, like where you kind of copy this. But GPT-4 is trained on that task, and that's why a lot of people use it. It's pretty good at doing things like this. And then another one, this looks really complicated, it's called chain of thought prompting. All it does is, ignore what is here right now, I'll just go back to the previous slide. What it does is basically, you just tell it to think. That's it. And it produces better results because you're like, think through the example first, and then answer the question. So the reason why this works is because when you're just trying to produce outputs that look like this, the training data is kind of like biased in a way. Like what happens is when you're feeding it back in every time, it's going to produce similar outputs that are like this. So if you train it on like the entire internet, there's going to be a lot of examples that are bad. So a lot of the more good ones are going to be ones where they reason well, and also those are going to be inputs back into the thing. So it tries to like produce good outputs in that way. So like, I don't know if that was a clear explanation, but like if it kind of knows what it's trying to say, it just kind of completes a thought in a way that is most probable. That was not a good explanation, but maybe I'll get a better explanation in later. But the idea is you tell it to think it through, and it thinks it through, and then produces the answer. So this is an example of like few shot, and then this normal few shot, which is a standard prompt, and that is the answer is 27, which is wrong. And here you have an example. I think in this example, they in their few shot, they basically had an explanation first and then the answer. So this one does it a bit differently, where they have an example that explains it, and then gives the answer. Another way of doing it is just trying to think through the problem first and then answer it. So this combines the previous technique and chain of thought. So if you want to take a look at it for a bit, you can. But the idea is here you have an example, and the output answer is an example of responding with an explanation. And this just basically helps it reason through the actual problem. All right, another big thing is something called retrieval augmentation. Sounds big again, but a lot of a common thing you'll see in large language models is these tasks or these big names of like performing better with LLMs. It's just pretty simple, straightforward things. So what retrieval augmentation means, sounds really complicated, is you just search up the internet and then you provide the information in the prompt. That's literally it. So when I code it up, it's literally just gonna be me searching up something on the internet, encode the thing into numbers, and then just wait. I'm just kidding. So that's one way of doing it, where you encode it into numbers. But one thing is just search it up on the internet, get the words in the Wikipedia, and just say, this is your information, and then the question. So that's like an example of a prompt that uses retrieval augmentation. And the main part here is like searching it up efficiently and like in a way that actually produces good results. So what retrieval augmentation nowadays does is like they encode all the information first, and then they use like a vector database to like search those semantic encodings. Semantic just means meaningful encodings in a way that they can like get good information. So it's like kind of Google search, but more efficient, I guess, or more efficient and meaningful way. And then once you get the most related thing, then you like put it into the prompt. So let me show you what the prompt will look like here. because it's probably more important to understand this, like the actual prompting stuff, because you're going to use it like that. I wish I had an eraser. I think it's on the other side. No, it isn't. Okay, so an example of this would be info. What I searched up on the internet. And then question. And then the answer. And this just tells the thing to answer right here. I mean, you don't need to do it, the answer part, but it's useful when you're doing examples to like divide it up. So I was just like, when was John F. Kennedy born or something? And like, GPT is probably trained on that, but like, if you ask more obscure questions, you would have to retrieve it from the internet and then put it into the prompt and then do that. So retrieval augmentation here, the example is you have a prompt and a query kind of, and then you query and you do search and you get the most relevant thing and then you put it into the prompt. That's basically what's happening. So on the prompting side, it's pretty simple. You just add it to the prompt. But the hard part is actually getting good information. And that's where a lot of innovation can happen nowadays, where they're trying to find information better. And a lot of different techniques for GPT to think through things more clearly. So to avoid like a lot of the hallucination, which just means it's just making up stuff. So that's kind of a broad overview of transformers, autoregressiveness, which is just like where you feed it back in over and over, and like common prompting techniques. So any questions so far, or any questions y'all have?
You say this only works on GPT-4?
This one? This works on anything that's a LLM. Like you prompt it, well, any language model that's trained in that task. So this is like, if you look at GPT-4 right now, they added like a Bing feature. This is what's happening. It's using Bing to search it up, I think. And it just plugs that information to the prompt. And similarly, when you like interact with it multiple times, since it doesn't really have a information state, like where it doesn't save data, what they do is they just attach previous conversation and they just feed it in again. So that's why like if your conversation gets too long, they kind of limit it. Or they might not have the entire information because the size of input they have is limited. All right, this is kind of like the main things I was trying to cover today. So you'd like to sign in and feedback. So hopefully y'all learned something today and you can use it. If you want me to go through an example, I can do that for y'all too. Let me know if you can't scan it, because I can move it around to make it more scannable. Sorry for like not being like having y'all do anything today. But yeah, maybe we're gonna have a follow-up workshop for this where we use an API to do this.
Does that mean somebody else with the right question, the engine daily gets smarter and you can get the same answer?
So it's not necessarily that it'll get smarter, it'll just produce better outputs.
So if another person asks the right question and another person asks a similar question.
There you go. So everyone can hear.
My question is, if two people are using the same engine and one person asks the right question, would that benefit the other person asking the similar question?
I don't think like they have the same conversation, but
So the conversation, the engine don't remember the other person.
Oh, no. So what you would have to do to get that information there is you have to put it back into the prompt. So as we kind of showed here, where the output was putting back into it, it would have to do that, but with previous conversation. So
The engine doesn't know about the other.
yeah, the engine wouldn't know about the other person unless OpenAI used that conversation to train their model. Then it might know, like, it might like produce the thing because it's most probable. Anyone have questions? Maybe like questions about like how companies nowadays are trying to use it? Because I might have some insight, or maybe Rami might have some insight.
Yeah.
Yes. Maybe like if you're wondering how GPT does something and you don't understand it, like I can explain it to you. All right, can you? Yeah, okay, thanks.
Okay, so I saw somewhere on the internet that like ChatGPT was like expensive to run, like it's expensive to run inferences.
Uh-huh.
But like there are other like LLM models that like aren't nearly as like
Expensive.
potentially expensive, yeah.
So the reason why it's expensive is because it's autoregressive, and every time you get one output, you have to refeed it back in and get another one. So it's like kind of like, so like let's say what you're expecting is like you just put it in once and you get the whole output. That doesn't happen. What happens is you get like one tiny bit of the output, you tack it back on, and then you do it again. So you effectively use the model like 100 times to get like 100 token output. So that's why it's like really expensive. And also when you make the architecture like 100 billion parameters, it takes like 100 billion floating point operations. And when you have that much, it's gonna be like really expensive to run. Because it's just like more compute. And then you have to do that like 100 times over because it's autoregressive. Did that answer your question? All right.
Is it possible to train an alien to write better code?
Yeah. I mean, it already happened.
Specifically to what you want,
What do you mean?
customize to your style of coding?
Yeah. I think GitHub Copilot does that.
Okay.
Hopefully that was helpful.
What about detecting the vulnerability?
Yeah.